11 o'clock. We're going to get started. Is it recording?
Yep.
Great. Good morning, everyone, for joining this this week's distinguished webinar series in AI and cybersecurity. Today's distinguished speaker is Dr. Gal Vardi, postdoctoral researchers from TTI-Chicago and the Hebrew University. The title for today's talk is on implicit bias and benign overfitting in two-layered neural networks. Dr. Gal is a postdoctoral researcher at TTI-Chicago and the Hebrew University, hosted by Nati, Srebro, and Amit Daniely as part of NSF-Simons collaboration on the theoretical foundations of deep learning. Prior to that, he was a postdoctoral researcher at the Weizmann Institute and the PhD student at the Hebrew University. His research focuses on theoretical machine learning with an emphasis on deep learning theory. Dr. Gal, it is an extreme honor to have you as part of the webinar series at the University of North Dakota. And I'm so delighted to introduce you. And then the floor is yours to start sharing your screen. You have about 40 minutes or so to give a talk. Thank you so much.
Thank you very much. Do you see my screen right now? Or,
not yet.
Should I share it again? Do you see it now?
Yes, we can.
Okay, great. So thank you very much for the invitation. It's a pleasure to be here. And in this talk, I will discuss implicit bias and benign overfitting in neural networks. And I will discuss several joint works with this list of great collaborators. Okay, so in this talk, we will have two parts. In the first part, we will discuss implicit bias and its implications. And then in the second part, we will focus on a related phenomenon, which is called benign overfitting. So let's start with the implicit bias. Neural networks in practice are often overparameterized, which means that the number of parameters in the network can be larger than the number of training examples in the training dataset. And in such situations, there are typically many different solutions that fit the training dataset. Namely, there are many different neural networks that perfectly fit the training data, but from this large set of possible solutions, some of the solutions also generalize well to test data, but other solutions only overfit the training data and do not generalize well. However, for some reason, empirically, it seems that gradient methods have some kind of tendency towards the good solutions. It seems that there is some kind of implicit bias toward the solutions that also generalize well. And understanding this implicit bias has been a major question in the theory of deep learning in recent years. And it is believed that understanding this implicit bias is a key to understanding generalization in deep learning. Now, in this part, I will focus on three main implications of the implicit bias. First, I will show that the implicit bias can lead to good generalization, which matches the empirical observation that I just mentioned. But then I will also show that the implicit bias has some negative implications on adversarial robustness and on privacy. But before I start discussing the implications, let's first introduce the general setting that we will discuss in this talk. So we will mostly focus on fully connected ReLU networks, such as the network in the figure on the left side. And here I denote the network by phi of theta and x, where theta are the parameters of the network and the x is the input. And we will train the network using gradient descent or using gradient flow, where a gradient flow corresponds to gradient descent with an infinitesimally small step size. So essentially, gradient flow is an approximation of gradient descent with a small step size. For example, here in the figure on the right side, we see the discrete trajectory of gradient descent, and we see a continuous trajectory of gradient flow, which approximates gradient descent with a small step size. So we will train the network with respect to some training data set, and we will consider classification, which means that our labels are either +1 or -1. And we will use the logistic loss function, which is a very common loss function for binary classification. It means that we run gradient descent with this objective given here. This objective is the training loss, where the function L inside this sum is the logistic loss function, which is stated here. Okay, so basically it's a very standard setting of binary classification with a fully connected ReLU network. And in the talk, we will mostly focus on this setting. And in order to discuss the implicit bias in this setting, I will start with some very simple definitions. So we say that the network is homogeneous with respect to the parameters of the network if changing the scale of the parameters is equivalent to changing the scale of the output. Formally, it means that if we multiply the parameters theta by some positive alpha, then it is equivalent to multiplying the output of the network by alpha to the L for some constant L. Now, in this talk, we will mostly consider two-layer networks. And an important thing to note about this definition of homogeneous networks is that this definition always holds in two-layer ReLU networks, even if we have bias terms. So if we have bias terms in the hidden layer, note that the network is not homogeneous with respect to the input, but it is still homogeneous with respect to the parameters. So basically, all of the networks that we will discuss in the talk are homogeneous. And we will say that gradient flow converges in direction to some theta tilde if, as the time t goes to infinity, the direction of theta converges to the direction of theta tilde. Now, since we train the network using the logistic loss function, then and since the logistic loss function is strictly positive, then the training loss cannot be exactly zero. We cannot reach training loss of exactly zero. And it means that when we run gradient descent or gradient flow, if the training loss converges to zero, it means that the norm of the parameters tends to infinity. So typically, the norm of theta will go to infinity, but since we will consider homogeneous networks, we will not really care about the norm of the parameters. We will only care about the direction of the parameters, because the scale of the parameters only affects the scale of the output, and it does not affect the sign of the output, and therefore it does not affect classification. So we will only care about the direction of theta. And for this setting, there is a known result by Liu and Lee and Jean Telgarsky, which says that in homogeneous networks, if gradient flow reaches some sufficiently small training loss after some finite time, then gradient flow converges to zero training loss, and it converges in direction to a KKT point of the max margin problem. Now, the max margin problem is the problem which is stated here, in which we want to classify all training examples correctly with margin of at least 1, and we want to have a minimal norm for the parameters. So basically, for each training example, we want the sign of the output to be to correspond to the label yi. We want the absolute value of the output to be at least 1, and we want to have a small norm of the parameter theta. Now, the theorem says that we converge to a KKT point of this problem. A KKT point is a stationary point of the optimization problem. Essentially, the KKT framework is an extension of Lagrange multipliers, where in Lagrange multipliers we can only handle equalities, and KKT allows handling also inequalities. But formally, a KKT point is just a point which satisfies some set of conditions which are called KKT conditions. So the theorem guarantees that we converge to some point, some parameter theta that satisfy these KKT conditions, which are given in these equations. And in this talk, we will not really care about the details of these equations. All we need to understand is that the theorem guarantees that gradient flow only converges to solutions that satisfy some set of conditions, some set of equations which are called the KKT conditions. And these KKT conditions are necessary but not sufficient for optimality. It means that it's possible that we converge to a KKT point, which is not an actual max margin solution. It is possible that you converge to a KKT point, which is not a global optimum of this optimization problem. So now, intuitively, we can think about the theorem as implying that there is some kind of tendency towards margin maximization because we converge to this stationary point, to this KKT point of the optimization problem. But formally, it is not guaranteed by the theorem. And indeed, it is analogous to the case of when we run gradient descent over some function and we reach a point where the gradient is zero, but this stationary point does not have to be a global minimum of the function. So here we have an analogous situation. Okay, so we know that the implicit bias implies that we converge to solutions that satisfy some set of equations called the KKT conditions. And now we want to understand what are the implications of this implicit bias. So I will start by discussing the implicit bias towards good generalization and bad adversarial robustness. And in order to discuss it, I will need to remind what are adversarial examples. So an adversarial example for a given input and a given trend model is a small perturbation, such that if we add this small perturbation to the input, we get a new input, which is close to the original one, and it looks to humans similar to the original one, but it is classified differently by the network. For example, we can have an image of a duck and add a small perturbation and get a new image which still looks exactly like the original one, but it is classified by the network as a horse. Now, these kind of adversarial examples are known to be very common in practice. So it seems that trained neural networks tend to be highly susceptible to adversarial examples. Namely, trained networks tend to be non-robust to adversarial examples. But from the theoretical point of view, it's not sufficiently clear why this is the case. And so empirically, on the one hand, as I already mentioned, it seems that there is some implicit bias towards solutions which generalize well. But on the other hand, it seems that there is implicit bias towards solutions which are vulnerable to adversarial examples. So it seems that the implicit bias might be good for generalization, but bad for adversarial robustness. But the question is whether we can actually prove that this is the case, and whether we can understand under what settings, under what conditions these phenomena really occur in trained networks. And in order to gain some understanding of these questions, as a first step, we will start by considering a relatively simple setting where we have a two-layer ReLU network and we have data that consists of clusters. So our network is just in this figure, a two-layer ReLU network, which is given by this expression. And note that we also have bias terms in the hidden layer. So these Bj are the bias terms. And so this is the model that we consider. And we consider a distribution that consists of K clusters. So our data distribution is a mixture of Gaussians. And it means that in order to choose a random example, we choose some index J between 1 and K. And then we choose the input X from a Gaussian with some mean mu J. And then the label Y corresponds to the cluster. So for each cluster, we have some Yj, which is the label that is given to all examples from this cluster. Okay, so it's a very standard setting of a mixture of Gaussians. And we will have some assumptions here. So we will assume that the norm of the cluster means of mu J is square root D, where D is the input dimension. So it corresponds to the case where each coordinate in the input is of size O of 1. And also, we will assume that there are not too many clusters, and the correlations between clusters are not too large. So this is a technical assumption, and instead of specifying the formal technical assumption, I will just give one typical example, and then when I describe the results, we can just think about this example. Suppose that we choose that we have at most square root D clusters, and that we think about each cluster mean as being a random vector on the sphere of radius square root D. And suppose also that the radius of each cluster is square root D, which means that the radius of each cluster roughly equals to the norm of the cluster mean. Okay, so in this case, with our probability, our assumptions will hold. And therefore, when I discuss the results, we can just think about this example where we have at most square root D random clusters on the sphere. Now, for this setting, we want to understand whether the implicit bias leads to good generalization and whether it also leads to bad adversarial robustness. So let's start with generalization. We have the following theorem. Suppose that the number n of examples is larger than the number k of clusters up to some log factor. In general, I will ignore log factors in this talk. Then we showed that with high probability over the training data set, if gradient flow reaches some sufficiently small training loss after some finite time, then it converges to a network that generalizes well. So basically, the theorem says that if gradient flow manages to reach small training loss, if gradient flow does not get stuck in some bad local minimum of the training loss, then it converges to a good network, to a network that generalizes well. And there are two important things to note about this result. First, the result is independent of the width of the network. So the width can be, the network can be as wide, can be arbitrarily wide, which means that in principle, such a network can approximate any continuous function. But still, the implicit bias implies that we can converge only to very specific solutions. And these very specific solutions are solutions that generalize well. And so the implicit bias prevents harmful overfitting. And also note that the sample complexity requirement in the theorem is that the number n of examples is larger than the number of clusters. And this sample complexity is optimal up to log factors because if we do not see an example from some cluster, then we cannot predict the label of this cluster. And therefore, we cannot hope to generalize well if we have less examples than clusters. So here in this result, we see that the implicit bias provably leads to good generalization. It provably prevents harmful overfitting. And it does so with an optimal sample complexity. So this is the result about generalization. And in order to prove this result, we use the fact that there is implicit bias toward KKT points of the max margin problem. And basically, we show that every KKT point in our setting generalizes well. And therefore, since gradient flow can only converge to KKT points, it means that it can only converge to solutions that generalize well. Now we also want to try to understand adversarial robustness in our setting. So in order to do it, since there is implicit bias towards margin maximization, then a natural question is whether margin maximization is good for robustness or not. And intuitively, if we think about the case of linear predictors, then in linear predictors, it is well known that gradient methods always converge to a solution that maximizes the margin. And in linear predictors, margin maximization is actually very good for robustness because maximizing the margin implies that we maximize the distance between the data points and the decision boundary, which is exactly what we want in order to get a robust network. So for the case of linear predictors, margin maximization is good for robustness. But the question is whether this intuition also holds in nonlinear neural networks. And we will show that the answer is no. We'll show that in nonlinear networks, the implicit bias can be highly non-optimal for adversarial robustness. And in order to show it, we will show two theorems. In the first theorem, we will show that in our setting, there exist networks which classify the data correctly and are also robust to adversarial examples. And then in the second theorem, we will show that although there exist such good networks, gradient flow cannot converge to such good networks because the implicit bias prevents it. So let's start with the first theorem. We show that there exists a two-layer ReLU network such that if we choose a test example, then with high probability, the example is labeled correctly by the network. And flipping the sign of the output requires a perturbation of size at least omega of square root d. Now, recall that in our setting, the distance between each two clusters is O of square root d. So it is obvious that we can move from a positive cluster to a negative one or vice versa with a perturbation of size O of square root d. And therefore, the best that we can hope for in terms of robustness is to require perturbations of size omega of square root d. So essentially, the robustness of the network in this theorem is optimal. Now, in the second theorem, we will show that although such robust networks exist, we will not converge to them because of the implicit bias. And more specifically, we show that every KKT point, namely every point that gradient flow can actually converge to, is such that if we choose a test example, then we can flip the sign of the output with a perturbation of size O of square root d over k. Okay, so every solution that the implicit bias allows gradient flow to converge to is such that there exists a perturbation that flips the sign of the output and has size square root of d over k. And therefore, if k is larger than a constant, then the robustness is non-optimal. For example, let's recall our example that we already mentioned, where we have square root d random clusters on the sphere, and the radius of each cluster is square root d. So if we plug in k equals square root d, we get that the size of the perturbation is roughly d to the quarter, which is much smaller than square root d. Okay, so if we have square root d random clusters on the sphere, then the size of the perturbation is much smaller than the optimal robustness that we can hope for. And therefore, we can see that the implicit bias leads to non-robust solutions. Okay, so to summarize this part about clustered data, we showed that the implicit bias provably leads to good generalization and bad adversarial robustness. Now we will turn to the third implication of the implicit bias, and we will show that in some situations, the implicit bias can lead to some privacy issues. Basically, we will show that the implicit bias might hurt privacy in some situations. And we will consider the question of whether we can reconstruct training data from the parameters of a trained neural network. We are given a trained network, and we want to reconstruct training data that was used for training this network. And the question is whether this is possible to do such a thing. And we will show that it is possible, and in order to do it, we will use the results about the implicit bias toward margin maximization, and we'll show that how we can use it in order to construct training data. And of course, the ability to reconstruct training data from a trained network might have negative implications for privacy, because in some situations, the training data can be very sensitive, and we don't want any user with access to the trained model to be able to reconstruct the sensitive training data given the trained model. Okay, so how can we reconstruct the training data? Recall that these are the equations stated here are the KKT conditions of the max margin problem. And the implicit bias implies that given some training data set, gradient flow converges to some network, to some theta that satisfies these equations. Now, when we want to reconstruct training data, we are given the parameters theta of the trained network, but we do not know the data set. And we want to find a data set that satisfies these equations with respect to the given parameters. So in a sense, we are doing the reverse process to the process which is done during training. And in order to be able to find the solution, to find a data set that satisfies these equations with respect to the parameters, we mostly use the first equation number 1, which is called the stationarity condition. And in order to find a solution, we run gradient descent over the objective given here on the bottom. And every solution which gives value of 0 for this expression is exactly a solution for equation 1. So we use gradient descent in order to find a solution for this equation. And this solution is the data set which was used during the training. And so let's see an example for reconstruction. Here we see, here in this case, we trained a model using 500 examples from CIFAR-10. Each example is an image of, is either an image of an animal or a vehicle. And we have binary labels of animals versus vehicles. And we trained a fully connected network with 3 layers. And then we, given this trained network, we tried to reconstruct the training data with our method. And here we see the reconstructions. In rows number 1, 3, and 5, we see the reconstructed images. And in the rows below them, we see the original images from CIFAR-10 that correspond to the reconstructions. And we can see that in this case, we have many high quality reconstructions. And also later we extended our reconstruction scheme also to multi-class classification and to convolutional neural networks. And here we see some examples for reconstruction in these settings. So I would say that our results show that at least in some settings, it is possible to reconstruct training data from a trained network. The main limitation of our results is that our training data sets are relatively small. Here I showed an example with 500 images. And if we try to reconstruct from larger networks, we were also able to reconstruct a data set of size 5,000. But even 5,000 is relatively small compared to what is used in practice, what is often used in practice. So a very interesting open question is whether we can extend our method also to more realistic settings. Okay, so now I will move to the second part of this talk, in which we will discuss benign overfitting. Benign overfitting, we say that we have benign overfitting if the learned predictor, on the one hand, interpolates noisy training data, namely, it perfectly fits noisy training data, but it also, on the other hand, it also generalizes well on test data. Now, note that here, when we consider benign overfitting, we consider noisy training data, which means that we have label noise. It means that the labels in our training data are noisy. And recall that in the previous part of this talk, we discussed a setting where we did not have label noise. And in this sense, understanding the setting here of benign overfitting is more challenging because of this label noise. And the notion of benign overfitting started from empirical evidence by Zhang et al. In their work, they trained an overparameterized network on some standard tasks with noisy data. and they interpolated, they perfectly fitted the training data. And the network generalized well also to test data. Now, this observation was very surprising because common traditional understanding in learning theory says that interpolating noisy training data is a very bad idea if we want to generalize well. So in principle, if we interpolate noisy training data, we should not expect to generalize well. But still, empirically, it seems that neural networks are able to generalize quite well, even when they interpolate noisy data. And starting from this empirical work, there have been a huge number of theoretical works that tried to understand under which settings, under what conditions, this phenomenon of benign overfitting happens. And indeed, this phenomenon of benign overfitting seems like a very fundamental question for understanding generalization in deep learning. Now, in order to illustrate this notion of benign overfitting, let's consider this simple illustration. Suppose that we have data which is labeled roughly according to some linear predictor, but it also has some label noise. In this case, the base optimal predictor is this linear predictor. This is the optimal possible predictor for this setting. Now, if we interpolate the noisy training data with some over-parameterized model, we can imagine two possible situations. One situation would be harmful overfitting, in which we interpolate the training data and we do not generalize well. And the other situation that is perhaps possible is benign overfitting, where on the one hand, we interpolate the training data, but the predictor that we get generalizes like the optimal predictor, which means that if we choose a random test example, then with high probability, it performs, it is labeled similarly to the optimal predictor. Now, of course, this is just an illustration. If we will train an actual neural network with this specific data, we will not get benign overfitting, but this is an illustration to understand the notion of benign overfitting. And one of the reasons that understanding benign overfitting and analyzing benign overfitting is usually challenging is that we cannot easily use the standard tool of uniform convergence, which is a very classical and useful tool for proving generalization. In uniform convergence, in order to use uniform convergence, we usually need to prove the uniform convergence property, which says that if the training data set is sufficiently large, then for every hypothesis in the class, the training loss is close to the expected test loss. Okay, so the uniform convergence property says that for every hypothesis in the class, if the hypothesis performs well on the training data, then it also generalizes well, and therefore it allows proving generalization. Now, so this is a very common tool that people often use, but when we consider interpolation of noisy training data, we cannot easily use it because of the following reason. Suppose that we consider classification, and we have some label flipping noise, which means that we flip each label with some probability p. In this case, the test error cannot be smaller than p, because we have this label flipping noise. However, if we interpolate the noisy training data, then the training error is 0. So there is a gap of at least p between the training error and the test error, and therefore we cannot hope to prove that if the size of the dataset goes to infinity, then the gap between the training error and the test error goes to 0, because there is this gap of at least p. And this situation makes our ability to use uniform convergence more challenging, and it makes the phenomenon of benign overfitting more surprising. Now, so in recent years, there have been a very large number of works on benign overfitting, and most of these works focus on linear predictors. namely either linear regression or linear classification. And in these works, it is shown that under certain conditions, when we train a linear predictor, we get benign overfitting. And our understanding of benign overfitting in nonlinear neural networks is much more limited. There are these two prior works on fully connected two-layer networks, in which they showed that benign overfitting occurs in a setting where we have two opposite clusters, one with positive labels and one with negative labels. And we also have label flipping noise, which means that we flip each label with some probability P. And they showed that under certain assumptions on the size of the cluster means and the radius of the cluster, we have benign overfitting. And in order to show it, they analyzed the trajectory of gradient descent, starting from the random initialization until convergence. And they show that it converges to a network that exhibits benign overfitting. Now, something which is worth mentioning about all of the prior results on benign overfitting, both the results for linear classifiers, linear models, and the results for nonlinear models, is that in all of these results, the data is high dimensional, which means that the input dimension is much larger than the number of training examples. And of course, practical settings are often not high dimensional, and therefore this assumption, which appears in all of the known results on benign overfitting, is a significant limitation of the existing results. And given all of these prior results that I mentioned, I want to discuss three main questions. The first question is whether we can show benign overfitting in fully connected neural networks in settings which are much more in distributions which are more general than this case of two opposite clusters. The second question is whether instead of analyzing the trajectory of gradient flow of gradient descent, we can prove benign overfitting in nonlinear networks using the KKT conditions of the max margin problem, which we discussed in the previous part. And third, is it possible to show benign overfitting also in settings which are not high dimensional? I will start with the first two questions. In a recent work, we showed that in two-layer leaky ReLU networks, we get benign overfitting in settings which are more general in distributional settings which are more general than this distribution of two opposite clusters that I mentioned. And in order to prove it, we used the KKT conditions of the max margin problem, and we showed that every KKT point in our setting exhibits benign overfitting. And basically, we showed it for two distributional settings. The first setting considers a mixture of K Gaussians. Essentially, it considers K clusters. And we showed that under certain assumptions on the size of the cluster mean and the radius of the cluster and the correlation between clusters, we get benign overfitting. And then in the second setting, we considered data which is sub-Gaussian, where each coordinate in the data is an independent sub-Gaussian, and we showed that under certain conditions on the covariance metrics, we get benign overfitting. And both of these distributional settings are more general than the setting of two opposite clusters in the sense that they include this previous setting as a special case. Okay, so this is one result about benign overfitting. Another recent result in a recent paper is that benign overfitting occurs in two-layer ReLU networks if the data has an XOR pattern, which means that we have two opposite clusters with positive labels and two opposite clusters with negative labels. So we showed that also for this data distribution, we get benign overfitting. And in order to do it, we analyzed the trajectory of gradient descent and showed that it converges to a solution that exhibits benign overfitting. And in this case, it does not suffice only to use the KKT conditions. We actually had to analyze the trajectory. Okay, so as we can see from these results, benign overfitting in nonlinear networks can occur in various distributions. But an important thing to mention also about these new results is that the data distribution, the data in these new results is also high dimensional. So even after these new results, all non-results on benign overfitting require high dimensional data. So we still need to discuss the third question about whether benign overfitting is possible in low dimensional settings. And in this respect, it is relevant to mention an empirical evidence by Malinar et al. They trained some overparameterized networks for some standard tasks with noisy data. And the data is not high dimensional in these tasks. And they showed that they do not get benign overfitting, but they also do not get catastrophic overfitting. And they called this intermediate regime tempered overfitting, which means that if we think about the limit where the size of the dataset goes to infinity, if we think about large training datasets, then the test performance does not approach the base optimal performance, which means that we don't have benign overfitting. But it also does not approach a trivial predictor. It does not, the predictor does not behave like a random guess. It behaves much better than a random guess. And so the predictor is not, the overfitting is not catastrophic. It's not benign, but also not catastrophic. And they called it tempered overfitting. And I think that if we combine this empirical evidence with the fact that all theoretical results require high dimensional data, it suggests that an important question might be to try to understand tempered overfitting with low dimensional data, namely to understand the test performance of interpolating neural networks in settings where the input dimension is smaller than the number of training examples. And as the first step, we already analyzed the case of univariate networks where the input dimension is 1, where d equals 1. And in the recent work, we analyzed tempered and overfitting in this setting, and we gave some characterization of tempered versus catastrophic overfitting in a regression setting with univariate networks. And also in another recent work by researchers from Weizmann Institute, they considered a similar question for a classification setting, and they proved tempered overfitting. So I would say that for this case of d equals 1, we already have a reasonably good understanding of the overfitting behavior, but already for d equals 2, we don't understand it. And I think that as an interesting next step, it would be interesting to try to understand overfitting in low dimensional settings, which are larger than 1, where d is larger than 1. Okay, so I will conclude. We said that the implicit bias seems to be a key factor for understanding generalization in deep learning, and we've proved that in some settings we can use it in order to actually prove that the neural network generalizes as well. And then we also said that the implicit bias is useful for understanding adversarial robustness, and we also said that it might hurt privacy in some settings. And then we discussed benign overfitting, and we said that in high dimensional settings, the implicit bias can lead to benign overfitting. And finally, we raised the question about understanding benign versus tempered overfitting in low dimensional setting. That's it. Thank you.
Thank you, Dr. Gal, for a great, insightful talk. I think we'll open up questions, but I think I'm going to ask some questions. I know that we had a speaker from Google who talked about over-parameterization. So it is known that over-parameterized model achieves lowest error benign overfitting, and we do know that bigger models are much more robust, and there are various theorems that justifies that. But your talk is very interesting. Can you talk about to see, have you looked into the covariate shift, in terms of training distributions? That in practice, training distribution is different during the deployment phase. So I was wondering whether have you considered any type of distribution changes or covariate shift, in relation to your results?
Yeah, it's a good question. So all of the results that I mentioned do not allow for distribution shift. At least the analysis does not allow for distribution shift. We did not try to analyze it under the assumption that there is some distribution shift. I suppose that if we have some specific assumptions about the shift, then it might be possible to analyze it, depending on what we want to assume about this distribution shift. But I actually did not try to think about this direction.
Okay. There's follow-up questions on this, well, you do talk about, this privacy issues, and even though we see that some robustness could be achieved through what you talk about, and I was just wondering, how do one should handle, privacy when we do want to care about, what we need to achieve in terms of
Right.
I was wondering,
Yeah.
because that's kind of a left out piece that how do you see, one should address that, and even though knowing that, yeah.
Yes. So first, I would say that even though I showed that it is possible in some settings to reconstruct training data, I also said that in realistic settings where we use large data sets, our current method does not work well enough. So I'm not saying that currently in realistic setting I can reconstruct training data, but it might be possible. And therefore, it's a very good question. How can you avoid such situations? So one possibility would be to use differential privacy when training the network. It would have some costs in terms of accuracy, perhaps, or computational costs, and it has some limitations. But this is an important line of work which allows for overcoming at least some of these drawbacks of training with standard algorithms without differential privacy guarantees.
How does one ensure the optimization process does not amplify or reinforce the bias?
So that every optimization method has some implicit bias because if network is not parameterized, then you have infinitely many possible solutions, and the optimization method somehow chooses one of these solutions, and so it must have some bias, which in some cases it can be easy to characterize it. In other cases, it might be difficult to give a mathematical characterization, but you always have some kind of bias. Now, the question is whether this bias is good or not good. I guess it depends on what your goal is and what's the setting. And here we show that it might be good for generalization and bad for privacy and for adversarial robustness. But essentially, for every optimization algorithm, you will always have some implicit bias.
Mm-hmm. Interesting. I think let's see if I look at other questions what we have here. You talked about this XR pattern, right? And is that the same data size that is a different use case, or is it the same data set that you are handling? Could you talk more about that distribution of plus and minus?
Yeah, so the XR distribution is a simple distribution that in recent years there are several works about this distribution because it's not linearly separable and it's relatively simple. And we showed that in this distribution, if under some assumptions on the radius of the cluster and the size of the cluster mean, you get benign overfitting. Yeah, so it's another, I would say, another setting in which another distributional setting, another set of assumptions on the distribution in which you can get benign overfitting in nonlinear neural networks.
You mentioned somewhere, talked about optimal sample complexity. I'm not sure I understood what that means, even though I have some idea, but could you clarify for our viewers to see what do you refer to sample complexity?
Yeah, I meant that we showed that the network generalizes well whenever the size of the training data set is larger than the number of clusters. So it shows that you don't need a very large data set. It suffices to have a data set of size larger than the number of clusters in order to generalize well. And this is optimal because if you have less examples in clusters, then you cannot hope to generalize well. Because if you don't see an example from some cluster, you cannot predict the label of the cluster. And so we generalize well with a small number of examples. And in this sense, the sample complexity is optimal.
Very interesting. I think there's lots of questions in this, in this area, but I think, people actually working on this area, or studying this bias varies trade-off, yes, over parameterization, leads to, we want to make sure it generalizes well. At the same time, there's exposes to all these, issues in privacy, and yet you want to have a good robustness. Yes, what is the targeted robustness that one has to achieve? And you talked about this big O notations of the square root of D over K, and that is, equal to at some point what O notation square root of D, that, in your simple two-layer neural network, framework, what you talk about, right? So to close the loop, as part of the last question, and people are trying to use different data set to come up with, how effective their generalization is, and yet, and we need to be mindful of all these, negative privacy concerns that these implicit bias is going to lead to, right? Do you want to, I know that, are there any work right now people are looking at other than the, more than the two-layer network, or how would you plan to extend your work? What are your other futuristic, steps that you're taking to extend this particular piece of work?
Yeah, so there are no works that extend the results that I showed for other architectures, but I agree that it is an important and interesting direction for future work. And so I think that it might be interesting to extend it both to deeper networks, but also to other architectures. For example, to transformer architectures, attention mechanisms, and these kind of architectures, which are very common today in practice, but the implicit bias of these architectures is not well understood yet. And I think it can be very interesting to try to extend these results to these architectures.
I think you nailed it. I think, yeah, it's required some more. But the KKT conditions that you talked about, the number of KKT points that you test these, is that something new that one has to continue that particular approach of using this sample KKT points? Or I'm not an expert on this. I'm just trying to digest what this talk is about. And at the same time, I've listened to a couple of folks on this topic. I'm still Yes, the big question that you asked was reconstructing the training data from trained classifiers. Is it possible if we can able to successfully characterize the implicit bias? Yes, you say it is doable with using some simple use case, what you actually have studied, which is a good piece of work. But, yeah.
So the question is whether the implicit bias towards KKT points is new or not.
Yeah, using the KKT approach. Yeah, that's something that people should actually.
So this result is from 2019, and it was extended in 2020. So it's relatively new, and it holds for whenever the model is homogeneous, which is a relatively weak assumption, but it does not hold, for example, in transformers. And therefore, this theorem does not, if we want to analyze transformers, you cannot easily use this result, and it would require more research. Yeah.
Okay, sounds good. Thank you so much, Dr. Gal, for your time today, and
thank you.
Appreciate for your time, and we will send you a nice flag and for your time of contribution. I think I would love to chat with you over sometime to discuss, to learn more and how we can act your work. Yeah, thank you.
Great, thank you very much. Bye.
Bye.